All right, I'm very excited to talk about this. This is a project that's been going on for a while, and I've worked with it with Olivia and other people. And this sort of the main results that we're talking about here, I don't join with Olivia. And I'm particularly happy to talk about this here because for me this project is a little bit of a love letter for hyperplane arrangements. And what better place to do that but in Japan, and the Japanese groups have sort of developed a big part of this theory. Okay. Let's see. So, in what is likely one of the best thesis titles in math, Facing Up to Arrangements, Zaslavsky 50 years ago found a way to count regions of hyperplane arrangements. So, you have a hyperplane arrangement here, and you record the incidence patterns of the hyperplanes in the intersection. We know how to write the Möbius function of the elements of the poset, we know its rank. If we add up the absolute values of the Möbius function, we get 9, which is the number of regions in the arrangement. If we add up the actual values of the Möbius function, we get 1, which is the number of bounded regions in the arrangement. And that is Zaslavsky's main theory. That's like a really difficult thing to beat in your PhD thesis, right? But it's sort of like the starting point of the theory, 50 years ago. Now, we can put the Möbius values together in a polynomial with respect to rank. And this is sort of a topological object as well. It encodes the Bethe numbers, so the complexified complement of the hyperplane arrangement. And we can see what happens in various examples. Now, sometimes the characteristic polynomial factors, and Zaslavsky's theorem essentially says that if you plug in -1, you're going to get a number of regions, and if you plug in 1, you're going to get a number of bounded regions. So if your characteristic polynomial factors, that means that the number of regions factors. And if things factor, we get excited in combinatorics because there might be an algorithm that explains whether 2 ways to do the first step, 3 ways to do the third step, etc., and then have all of the objects that are counted. Now, if we start with a graph, we can construct a graphical arrangement where we take the hyperplane's assignment is equal to 0 just for the edges in the graph. And I'm giving you here the complete graph in 4 vertices, which corresponds to the braid arrangement, and has a nice factoring characteristic polynomial. And I'm giving you another example that also has a nice factoring characteristic polynomial, but it doesn't always happen. If your graph has a place where it could have a chord, but doesn't have a chord, it means it's not chordal, and in those cases the characteristic polynomial doesn't happen, or likely doesn't happen. In every other case, it factors, and you can read the integer. When I say factors, I'm using the combinatorial definition, which means factors in integer roots, or factors in positive integer roots. So you can even read those positive roots by sort of nice filtration of the edges of the graph that corresponds to complete elimination. You can also see in the picture that I've labeled some of the regions with acyclic orientations. So in examples that we care about, the regions of hyperplane arrangements have nice numerology, and they also have labelings by combinatorial objects. Okay. The C arrangement. So the C arrangement is a particular type of a deformation of an arrangement. Deformation is a weird word for arrangements, but we call it deformation of an arrangement something where you start with the hyperplanes of the central arrangement and you add parallel copies of them. You add however many parallel copies you want, and you put them wherever you want parallelly, right? All of these are deformations. The C arrangement is a particular deformation where, apart from x minus x is equal to 0 for all ij, so it's the complete graph, you also have x minus x is equal to 1. So this is a deformation of the braid. Now, C, we're studying it in terms of the Castanucci theory, but he found out that the number of regions is a beautiful formula. It's n plus 1 to the n minus 1. Number of bounded regions is n minus 1 to the n minus 1. So we love this number. One of the first things that we teach in an intro to combinatorics class or graph theory class is that there are n plus 1 to the n minus 1 vertex labeled trees. In fact, we can label the regions of the C arrangement with trees. This is the example. And we can label that with other objects that are counted by n plus 1 to the n minus 1. One of the favorite ones in this audience is the parking function. Okay. We have a labeling by Athanasiadis Linson, we have a labeling by Parker and Stanley, we have a labeling by Bernardi, we have a ton of labelings. We really love this arrangement. The characteristic polynomial is t times t minus n to the n minus 1. That was proven a little bit later by Hidley, inductively. There's another deformation where, apart from setting x minus x is equal to 0 and 1, you also consider minus 1 so that you have a symmetric picture. This is the Catalan deformation because it has n factorial times Catalan of n many regions. They're labeled by Hertz because I like the Catalan numbers. This is a pattern. So I work a lot with French mathematicians, and they tell me that it's imperative when you write a love letter for it to be elaborate. So there are many things that I like about the series. It has a remarkable proof. The C arrangement is a sub-arrangement of the affine arrangement, which means that you can label each of its regions by the alcove that is closest to the origin. The alcove is an affine permutation. An element of the group has an inverse. If you take the inverses of those C alcoves, it turns out ridiculously that they pack together in a simplex. A simplex of size n plus 1 is going to have n plus 1 to the n minus 1 elements. So the C region, the C arrangement has n plus 1 to the n minus 1 regions. If you do the same thing for the Catalan deformation, you're going to get the shape which is exactly like what you had before in the simplex, but now for every chord like this point, you have a complete permutahedron-like object around. If you haven't noticed already from the handwritten slides, you must believe me now that I was a student of Vic Reiner because I like things that generalize to veil groups. The C arrangement generalizes to all veil groups. If you start with a veil group and a set of positive roots, the reflection arrangement is the hyperplanes that cut the reflections. Alpha comma x is equal to 0. If on those you add the same equations but equal to 1, you get a generalized C arrangement. If you further add those that are equal to minus 1, you get a generalized Catalan. These are well studied and they have remarkable numerology. The characteristic polynomial of the reflection arrangement itself again factors with positive integer roots, and those roots, the AIs, they're called the Euler-Solomon. The AIs are called the exponents of the group, and they have differential geometric and representation theoretic interpretation. They're related to the degrees minus 1. They will appear a lot in formulas later on. Now, these arrangements for the classical types and for all veil groups, they were studied by many people starting maybe in the early 90s. So Athanasiadis in his thesis did a lot of this work, then Headley sort of managed to prove all of the C arrangements, then Yoshinaga gave better proofs for all of this. So you see that the characteristic polynomials, both of the C deformation and of the Catalan deformation, factor, which again is surprising and also means that the number of regions also factors. Another thing that I want you to observe here is that there's a sort of shift pattern. So from the reflection arrangement itself, whose polynomial is the product of the T minus I, to the Catalan arrangement, let's have a shift by 8. 8 is the Coxeter number of the group, or the biggest of those exponents plus 1. So there's like a sort of shift pattern that happens when you move from reflection to C to Catalan. I'm giving you here a picture of the type B arrangement. It's indexed by another favorite combinatorial object, which is anti-change in the root poset, and the coloring sort of records certain symmetry. A 6 by 8 phenomenon, it also has an interpretation that is Erhard theory. These pictures here give you a way of understanding the characteristic polynomial as counting points of a finite field that live outside of your hyperplane. If you rewrite your arrangement a little bit, so here both of these are written in terms of the Colway coordinates. Everything has just integer coordinates, and the finite field method becomes equivalent to counting points inside a box, inside this parallelogram and outside of the hyperplanes. It's very easy to model that with Erhard theory. The both cases for the reflection arrangement, or then for the Catalan arrangement, and everything sort of looks the same in its region, and so every region contributes the same Erhard polynomial, and this ends out after Athanasiadis to explain this sort of shift pattern between the Catalan and the reflection arrangement. This is work by Masahiko Yoshinaga, who realized that yes, it is more difficult to do it for the C arrangement because every little alcove that remains inside is of different sizes, but there is a nice partition of these sets that sort of explains what are the different dilation factors that you should consider. So yes, Masahiko Yoshinaga generated in this way this sort of theory of vorticity partitions that has been very popular. All right, so we said without the C deformation, I'm going to give you a new family, new in quotes. It's going to become really new in a little bit. So I'm going to give you a family of generalizations of the C. So we start with R parameters, integer parameters, and magnitude R. And we consider this deformation. Xi minus xj, it used to be 0, 1. Now it's going to go from minus ni plus 1 to nj. there are ni plus nj hyperplanes here. Right? That's like a null parameter generalization, null parameter family of C deformations, of C-like deformations. You can do the analogous thing for the Catalan one. Instead of going from ni plus 1, you're going to go from ni. This is more symmetric, but it has ni plus nj plus 1 hyperplane. Now, it turns out that both of these generalizations, all of their families, they have really nice characteristic polynomials which factor, which again means that the number of regions or the bounded one factors in nice small primes, which suggests that there is a nice combinatorial labeling or enumeration. Another thing that's interesting is that the roots in the C case are just the same number. It only depends on the sum of the ni parameters. Even though, as I'm showing in the pictures, the deformations are really different. This is the deformation that I get for parameters 1 to 3. You see you have 3 lines here, 4 lines, and 5 lines, all of the partial sums. And this is the one that I get for 1 for 1. I have only 2 lines here. These two arrangements are clearly different, but they have the same characteristic polynomial, hence the same number of regions. The Catalan deformation still only depends on the sum of the ni's, but you see it has this extra minus I here to model the formula of the previous one. Now, Athanasiadis considered the Catalan case in the 90s, and with Olivier, we proved these formulas. I knew how to prove them algebraically, but we did it together combinatorially. Then I realized that Nagashima and Tsuji had also proven this in a maximum general case, but they had proven it algebraically. So they did at first. Our proof was combinatorial, which was interesting, but at the same time, their paper helped me a lot because they were phrasing things in terms of restrictions, and I knew how to generalize this problem for variables. So you see, when you read this generalization, you're probably thinking, okay, so this is a generalization for SR, right? Because you have the braid arrangement for SR, and instead of xi minus xj 0 and 1, just have some extra parameters. But I'm going to convince you now that it's not for SR, it's for the sum of the ni's. So I'm going to talk a little bit about restrictions of hyperplanar. And I'll be doing the section which is called the flat. The restricted arrangement is our ambient space is the flat X itself, and we're intersecting the flat with all of the other hyperplanes that live around. This is going to give you a new hyperplane arrangement that lives inside the flat X. Now, it turns out that for reflection arrangements, all of the intersections have this cool property, which is that they're characteristic polynomial factors with positive integer roots. These positive integer roots are called Orlick-Solomon exponents. They're really cool. They have representation theoretic interpretation. They encode the degrees in certain submanifolds on the flag manifold for the reflection representation. For like their top homology has a copy of the reflection representation. They have they have interpretations in terms of wall crossing formulas. For now, I'm going to use them in the formulas that come up later on, and I want us to remember them as the positive integer roots of the characteristic. There's another invariant that is really important here, and it's not well known, so I want to take a little bit to talk about the new thing. So this is something that I like to call the relative Coxeter number. It was first explained to me by Antonin Fagin and Strahan 5 years ago. They did it, they worked on it in terms of Frobenius manifolds in the differential geometry. But it's really simple and Coxeter theoretic. If you have two flats, and one of them is codimension 1 beside the other, so Z is just a little bit smaller than X, then they correspond to two parabolic groups. The stabilizer of Z is a little bit bigger than the stabilizer of X. So the stabilizer of X is a product of irreducible groups, and some of them crash together to a new irreducible group in Z. Okay? So the bigger group only has one component that doesn't exist in W sub X. The Coxeter number of that component is what I call the relative Coxeter number of the interval X. If you imagine in a big braid arrangement a two-dimensional flat and its restriction there, that would correspond to a subgroup of the form Sn1, Sn2, Sn3. Now, this one is a braid arrangement, it's isomorphic to a braid arrangement B2, so it just has the three hyperplanes, x1, x3, x2, x3, x1, x2. And the first one corresponds to what happens when I merge Sn1 and Sn2. When I merge these two, I'm going to get an Sn1 plus N2. Right? So the Coxeter number of Sn1 plus N2 is N1 plus N2. Right? So these parameters Ni plus Nj that appeared before, I really want to think of them as the relative Coxeter numbers of one of my restrictions and some of its hyperplanes. I'm giving you an example for an restriction of V6. This is going to come up afterwards as well. I just want to point out here that the numbers are not that simple. There is no Ni and N2 pattern, right? So this horizontal flat is a flat of type A1 cross A4. In this particular flat, it is 6. So this has 4 simples that we took the intersections to get the 2-dimensional flat. And here I'm adding another one, and I'm adding another one, I'm adding this one, and I get this component, and this one really was isolated. So when I add a new vertex, there's sort of an active new irreducible component, the one that does not appear in W sub x. And this one here is of type, what is it, 1, 2, 3, 4, A4, so it has Coxeter number 5. So that would be the relative Coxeter number of that horizontal line. My point is that it's a Coxeter theoretic property that's easy to compute, and it's a good generalization of the Ni plus Nj, which wasn't really about SR, but about the restriction of the preference. So this is our theorem, or one of our main theorems with the lever. So I'm going to forget about this for a little bit and scan the slide this way. So I'm generalizing all of these braid deformation results. In the first setting, it's for the parameters examined 6a between minus Ni plus 1 to Nj minus 1. Here is the C case, and here is the Catalan case. Now the last one and the first one look the same, but it's an accident that they behave the same in the symmetric group. It has to do with the fact that the Euler-Solomon exponents are an arithmetic progression. Let's see what the generalization looks like. So this case I'm calling the Catalan minus case. All of the 3 deformations are constructed like that. I have a special flat that is an affine flat, and I'm intersecting some arrangement with that flat. In the first case, I'm intersecting the reflection arrangement. In the second case, the C arrangement. In the third case, the Catalan arrangement. Right? 3 cases. Now the flat is, I'm taking some subset of my simples, and I'm not taking the linear simples, but those that have equation alpha comma x is equal to 1, right? So I'm taking the simples, but the affine ones. So I'm intersecting those, and that determines a sort of flat. If I take that flat and intersect with the whole reflection arrangement, that gives me my Catalan minus deformation. With the C arrangement, it gives me the C deformation. With all of the Catalan arrangement, it gives me my Catalan plus deformation. So in the 3 pictures, it is easier. This blue horizontal line is the flat that I'm describing here, the standard flat, which is the intersection of some of the simples. I'm intersecting the horizontal line just with the reflection arrangement. I get 1, 2, 3, 4 regions, because the characteristic polynomial is t minus 4 minus 1 is 3, so t minus 3, so it has 4 regions. Here I'm intersecting the C arrangement with the horizontal line, and I have characteristic polynomial t minus 4, 5 regions. Here I'm intersecting the whole Catalan, right? I have characteristic polynomial t minus 6. So the construction is going to look a little bit better afterwards, but I want to observe the structure of the theory. We still have this sort of shift phenomenon, right? The Coxeter number appears again, but now a power that only depends on the flat. And these Euler-Solomon exponents appear again. Here it is h plus Bix, here it is h minus Bix. It models a little bit the theorem that Yoshinaga, that we described before, where we went to the Catalan deformation having h plus Ei. These are some cool pictures. These are the things that you get when you have the rank 2 restrictions of V6. Now, these are all of the different types of rank 2 parabolics in V6. And these are what the deformations look like for the C case. Now, notice how different all of these are. And notice in particular that this one has only 5 directions. So if this is a deformation of something, this is a deformation of a rank 2 arrangement with 5 lines, which can never be crystallographic. So I have a deformation of a non-crystallographic arrangement that seems, according to our theorem, has a characteristic polynomial that factors. It was very unexpected. Not only that, if you look very closely, so here, those hyperplanes are equally spaced, but here we jump away. So all of the hyperplane arrangements that we described before, the C and the Catalan, the hyperplanes were equally spaced with each other. In this one, they're not, and part of the difficulty is that they're part of a bigger lattice, and I'm intersecting it with a particular flat, so there's no reason that they would be equally spaced. But it was very difficult to construct an arrangement like that because I couldn't guess where they would be spaced. I was assuming that everything would be equal. So when I read Suze's paper, I realized that the restriction approach would be better and it worked. And the other thing that I want to talk about is that remember before I was saying that these relative Coxeter numbers play the role of an I plus and J. Well, if you believe me that these are the ones that I calculated, you will see that the number of parallel hyperplanes that appear are exactly the relative Coxeter numbers. 5 hyperplanes here, the relative Coxeter number is here, 5. Right, so these relative Coxeter numbers generalize these numbers ni plus and j that we had before. So let me say a couple of things about the proof. This really cool argument that we described before, where every affine permutation went to its inverse and they all back together in a simplex, this sort of also tells you how to label regions with Parkin functions. This is a bijection that was started by C that eventually Marco Thiel sort of clarified. We can keep track of each of the steps of this bijection and sort of think of a region in the big arrangement that is sort of close to the flat that we're intersecting with, and what Parkin function it corresponds to. These dark red Parkin functions, they all have the second and the third coordinates equal. These Parkin functions are fixed by the transposition to 3. All of the regions that we construct in the sort of intersecting with a simple flat here, all of these regions are labeled by Parkin functions that are fixed by W sub x. Because we understand the W action on the set of Parkin functions, we know how many regions there are. There are h plus 1 to the dimension x such regions. Knowing the Parkin function representation tells us how many regions are in our restriction, and then a recursive argument allows us to compute the characteristic polynomial. This recursive argument is similar to work of Hidley, so we sort of relate the characteristic polynomial of the deformation with the characteristic polynomials of deformations of localizations, right? But you have to show that the same formulas are true for the Coxeter numbers, right? The same recursion is true on the formula side. And I knew that from former theorem W Laplacian operator. So this is a difficult thing, but it was merged together with the recursion, and it's a little bit of a new way of proving formulas for characteristic polynomials. I want to say 2 things about freeness and multi-arrangements, but I'm going to go a little fast here. Freeness is a differential geometric notion, and it says that instead of thinking of hyperplanes in a discrete geometry fashion, think of them in the plane and consider a collection of polynomial vector fields, those vector fields that are tangent on all of those hyperplanes. This is a picture of the B2 arrangement, and this is a vector field that is tangent to the arrangement. Its equations x1 to the third partial x1, etc. If you consider all of those vector fields, they form a module over the polynomial algebra. If that module is a free-ish module, then we call the arrangement free. It turns out that often to be free is related with combinatorial characteristics of the arrangement. It's also very much related with deformations. You see, if you start with a deformation and you take its cone, if you intersect with a special hyperplane of the cone, then all of those hyperplanes that are parallel to each other sort of crush together in a single hyperplane, and you can consider it with multiplicity equal to how many hyperplanes you have, right? So a deformation has the information of how many copies I got of a hyperplane, which is like the multiplicity, but it has more information, tells you where to place the hyperplanes as well. So when you count vector fields that are tangent to the hyperplanes, if you say I want higher degree of tangency, it's like considering the hyperplane many times. And in the deformation, you also know where to put it. Here, we just consider it many times, but it's differential. It's a very big problem in the theory to figure out for a particular hyperplane arrangement which multiplicities are free. There is work by people in Japan, by Terao, Ritsan, Yoshinaga, Abe Terao, Abe Yoshinaga, then Christian came into the picture with Hogeman and her as well. All of these results had the characteristic that the multiplicities were either constant or almost constant, but they were working for all reflection groups. And they had shown that these are indeed free multiplicities, and they had like very good information about the degrees of the generators of those free models. Abenoida and Numata, and I think this was part of a former Fipset presentation as well, proved that for the braid arrangement, the ni plus nj is a free multiplicity. Our main theorem as far as freeness goes is that for any flat x, the restriction alpha sub x has a free multiplicity that is given by the relative Coxeter numbers. This is the first free multiplicity that sort of first also has to do with restrictions of arrangements, so sort of like non-crystallographic arrangements or non-reflection arrangements, and the multiplicities are different from each other in a serious way. Again, all of these are constant or almost constant. The proof is the most difficult part of the project, and I'm not going to talk about it. I'm only going to say that it behaves similar to addition-deletion theorems. It's just that there is a new theorem developed by Avedra-Wakefield about those, and when you restrict, the new multiplicity that you create here is really complicated and depends a lot on a parabolic rank 2 case, which rank 2 multi-arrangements are always free, but we don't know how to compute their exponents. Even though we don't know how to compute their exponents, in special cases we can do things like that. And here I was using a lot of work of Babel with creative tools on how to be able to do that. The conjecture here says that not only these multiplicities are free, but also when you subtract one and add one, and this subtracting one and adding one correspond to the Catalan minus and Catalan plus deformations. I cannot prove the freeness there. I tried it a lot with Kristen Stuman and Mr. Fagin for many years, and well, I'm offering an award. So far, I have been offering $42, but I figure since I got a tiny transposition, it's only fair to go for $132. And this is a small print, you don't have to worry about. So these are pictures of the free multiplicities that correspond to the 5 rank 2 restrictions of the A2 arrangement. Again, you can see here that the multiplicities are really different. Okay, so I had another slide where I was talking about future work and ideas, but you can ask me about it. I'm going to stop with that. Thank you very
much. Thank you, Theo, for the wonderful talk. Time for maybe a quick question. Oh, there we go.
So is this an actual file group and basically root system property, number counting, or is it actually a Cox group property?
So that's a good point. The deformations only work for the veil groups because the way that I define the deformations here, the way that we define the deformations on one of the things that work, is that I have to start with the C arrangement of the Q group or the Catalan arrangement and restrict it somewhere. The non-veil groups do not have C deformations and Catalan deformations, or some that work, so I cannot do them there. As far as the multi, So as far as the multi-arrangement results work or go, so this conjecture and this theorem, the theorem works for reflection arrangements, and this conjecture, I can also state it for reflection arrangements. There might be a version of those for complex reflection groups as well, but I'm not sure exactly what it's going to do.
Hasn't anybody tried to characterize the hyperplane arrangements that do have these nice factoring properties?
You mean that have the hyperplane arrangements?
The characteristic polynomial is real rooted that way. The roots mean something.
All right, so that's a really good question. It's very broad. So certainly, generally, which hyperplane arrangements have characteristic polynomials that factor has not been characterized. All of the arrangements that are super solvable have this case. All of the arrangements that are free, of course, have this case, right? What is true is after, let's see if I can find it. So after Yoshinaga's sort of brilliant work here, there was a huge amount, and I think it's in the Japanese school about generalizing the Gorpitsky partition thing. So here it's like which sub-arrangements of arrangements like this have a nice property in cutting sort of like smaller polygons here in a predictable way. And those arrangements in the symmetric group case generalize the chordal ones. It's a weaker property, so you can be chordal. You don't have a characteristic polynomial that factors, but you have the shift property. So there is a direction there, but otherwise, even in the restricted case, which was really well studied, it was unclear that it was possible. That's why I was happy with the result.
Okay, let's thank Theo again.